All right. So today we will quickly wrap up Digital Rocks portal. One thing that as a storage solution, so there is to any kind of database nowadays, there is the actual storage in the database. So you have certain information that is stored in the database. But key new development of where things are going is linking different databases to work together. So if you would have something that stores the data, if you can link it to a simulation or multiple types of simulation relatively seamlessly, that would be great, right? So where we are going in general is integration of all of the different data sets. And of course, in petroleum engineering or subsurface engineering in general, we have this extreme length scales and time scales that are away from each other, so it's not necessarily an easy thing to do. But that's kind of the goal of a lot of software solutions these days. It's going toward integration of different data sets. So in that vein, in Digital Rocks portal, you have probably seen in some of the volumetric data sets that have been uploaded, there's this action. So I have already seen, like, you can view a movie through the stack. And then there's this option of viewing things in ParaView. Right now, this is not going to work. I'm going to get a server error, but basically you connect to a supercomputer and the data is loaded on that supercomputer, and you can open software on the supercomputer and view the data set. Now, if the data set is small, it doesn't do much for you, really. But if data set is large, that could be potentially, you could have a data set that there's no way you can open on your laptop, but you can on a supercomputer. And here and there, sometimes you just don't want to deal with installing the software on your laptop, okay? But you go to a machine where it's already installed and you're viewing things through the web browser. So I'm going to show you, at some point I recorded a video of this process. So I'm going to play that video now. I'm going to up the volume. So this is posted on YouTube and the link is in your slides. I did post all of the slides. Okay. Is it actually playing? I don't hear anything, do you? Barely. I normally yell, but I use my low voice.
This is the image that I want to see. Basic information about the image, the height, number of slices is right here. There's one piece of additional information that is within the project description, and then this is the data is in the form of 16 bit, which is 2 bytes signed integer. Okay, so we are going to pick an action. You can actually view this image just by simply viewing the static movie of it, and this is walking through all 450 slices. You can also check out the histogram, so this gives you the idea of the data range, which in this particular case is roughly about -200 to 8,000. There's very little here, so basically the bulk of the information is here up to, this is 4,000 or so. In any event, we're going to see view the pattern, and we're going to connect to the supercomputer. Click on I know the drill.
And it takes a moment to open the connection. You can see that it's waiting for it. It has the schedule.
Wait.
And wait. Oh, Okay.
I'm going to quickly try development version report.
I did not bother to edit this out just to make it realistic. So just wait if it doesn't connect. This is the standard stuff of
And you can
connecting.
see that the job is being submitted to the parallel machine. Whenever you have a parallel machine, you do need to get into the queue. And this can take a moment. So I'm going to click now, connect to remote job. And you see a so-called ENC connection, and the Power View is open on this remote machine. So let's now try to find where is this data. It is right here. Let's just check what is it, the test, nothing in the test. So this is actually the data set downloaded to this machine. This is a raw data set, so
We're gonna work on ParaView later,
open the correct
but this is a software for 3D visualization.
raw binary files. Okay. And I will confirm once again that this is raw binary file. And after that, I actually have to enter the information about this image. Short is unsigned 2-byte integer, so that is correct. It is big endian as per Digital Rocks portal, and the only thing I have to do is enter data extent, so 349.
So the data size was
0 to
350.
349 gives me 350 dimension. Oops. 349. 449. And the rest is correct, so I'm just going to pick, I'm going to say apply now. So what you see in display is the outline, and it's a correct outline, but what we need is, for instance, volume. And this is essentially my data set. Now, if I wish, I can actually slice it. And there is first slice. It's an extract plane. Right now, we are looking at the 224, slice 224. You can walk through slices. I can also go back to my volume, and I can also do, just to check what the extent of the image is, I can do a quick filter, which is histogram. And for histogram, I would like more than 10, it's 256 is more appropriate here, so I hit that line. I will actually get the histogram of the data, but not so much granularity as we saw on the web page. But this is enough for me to investigate. So here, somewhere around 1700, 1600, there is like a minimum between these two peaks, that is a good place to visualize the surface between this population and this population of rock cells in the image. So let's try to do that. I'm going to delete this histogram. You don't have to, but I'm just going to make space. So, if it allows me to so now I'm going to pick contouring. You can also go to filter common contour. Either way, and here you have to actually pick which contour you will see. So let's say 1700 for instance. And then hit contour. So this is essentially the contour, and when you click offset mode, visualize the volume data set, that we can visualize things at the same time. And I'm just going to pick slightly different color for this surface. So let's say let's put something a little more orange. Texas burnt orange and close enough. Change, and this is it. Now let's say that I like this, the way it looks, and I want to take a snapshot. You have to remember where to save screenshot, and showing this is fine. And I'm going to say this image, so I will put it in my job. So it is in this is the name or number of the job that is currently running. So I'm just going to say screenshot of the surface. Okay. So this is now question is, how can I get this surface image? I can get this surface image. I go back to it should show up. In my scratch space. So this is the and this is where the image should show up.
So it takes a moment to transfer images, but basically under the job name or job number, you get anything that you saved in that remote session.
So essentially, you do have to remember in the scratch space, you have to remember a little bit about the date of the job and what was the ID. So they are slightly, they look random, but these are not the random numbers. These are different directories from different times I was trying to connect to the image. So, this is where it's going to show. And then I'm going to
That's about it. So this is essentially a remote desktop connection. All of you use remote desktop, correct? It's just that in this case, you're remote desktop into a parallel machine that has much better capability than any of the individual computers you could use. That's one thing, and you're connecting through your browser. So web browser, yes.
The histogram that you showed us, what was it? The histogram of?
It was histogram of the data.
Grain sizes?
No. Histogram of the actual, it's an image. An image have grayscale values, so it's histogram of those grayscale values. Now you see two distinct populations, okay? And because of, so basically, it's this project right here that I was exemplifying.
So one will be showing actually grains and one showing pores.
Oops, this is, yes, so one of those populations is pores and one of those is grains, and that's gonna be what we're gonna work towards because you want to identify them, and that's called segmentation. So that histogram is actually shown here as well. It's just it was slightly different format in ParaView. In part because ParaView is limited to 256 bins. And if you have 256 bins on the range of 8,000 of data, where most of it is not used, then you get different, like you don't get this level of detail as this histogram here. So that was the only thing, the limitation. But basically that, so the darker phase is this and the lighter phase is this. So these are the grains and in that image, and these are the pore spaces. Okay. And you can place a surface, and we're going to get through this. This is basically our quantification on of images that is coming up. And then the final thing is that whatever you work on, you're working on a remote machine. How do you get it back? Okay, you're not working in your own, you don't have a TAC account that you're working in. You're working in my TAC account, which was set up for this project. Okay, so everybody is working in the same TAC account, and then basically there is scratch space right here. So right now it's empty because it has been emptied since, but basically this is where those files show up, and anything that you save is under the directory with the job ID. So if you save a screenshot or you save the data or you, in some way you save something from ParaView session, that's going to show up here for you to download. If you're working on a publication, for instance, that little surface, right, that screenshot you might need for your publication, and you can transfer it back. So the idea is that in this remote session that you open on the machine, you're going to create some data, and that's going to show up in the scratch space here. And it, of course, it periodically gets emptied out. So I haven't done this since because the remote visualization has been on the move. Okay? Questions? Yes?
Why the screenshots are saved here?
You visualize something and you visualized it on a parallel machine. And now you want that screenshot. How are you going to get it? We have to post it for you. Because you're working in an account you cannot log into directly. Okay? It's not your TAC account. You have a TAC account. It's not your TAC account. It's mine. So I have to find a way to actually mirror it back to users. And basically it records, oh, it was you opened, you have to be logged in on the website, on the DigitalWorks portal. You have to be logged in. So it knows it's you that connected. And it has that job ID, so it's going to make it visible to you. Okay? So that you can download, because you might be working on a publication and you need a nice screenshot to put in that publication. Right? Or any other data, you might transform the data in some other way. So the idea is that you can, of course, this is a smaller data set, so you could simply work on your laptop. But for larger data sets, or maybe you don't have the software that might, so there's actually 2 videos if you want to replay. It's not the most exciting. I normally yell and I'm very loud, except when I'm recording a movie to myself, I'm talking only to myself, and then suddenly I have my low voice in there, and then I don't. So it's a little bit of a monotone voice. And then if you, so this is using remote visualization, or you can just download the data and open it to ParaView, and that's something that we're going to be doing in this course as is. Okay. So there's some other things that we have to consider when creating these portals, is that your data should be, just because you place it online, that doesn't mean that people will use it and be able to find it, and you have to ensure that things are findable, or discoverable is actually the term for information. So we are registered with Elsevier. Elsevier is a lot of journals are. It's a publisher. Geoscience Data Journal. This is where you can actually just go publish a paper just about your data. Okay? We're registered in registry of 3D data, Re3 data, and Synergy. So basically, there's like a little bit you can search for Digital Rocks portal in there. There's also user agreements. So just like always, whenever you do something online, you're kind of signing up for behaving online, and you're not gonna use Digital Rocks portal for any unintended purposes, whatever those might be. So please don't store your own photos or anything of that sort out there, because if I do have access to all of account, if one of the administrators finds these, they just delete them on the spot. Okay. So it's supposed to be only for work data, not any other data. So, and there's a whole lot of things that you sign up for. So you can actually read a whole lot of legalese over here, the language that lawyers work with. Now, this just for all of these pieces to work together, for remote connections to open, for different machines to communicate, there's a whole lot of, and all of this software is actually free that goes into building a portal like this. So there's this application layer. Of course, this is just the website. So there's HTML5 and JavaScript. Then there's administration of the database. There's Django. You open Docker, so you can open instances of various software such as ImageJ or ParaView and so forth. There's Python working behind. There's a number of other things. Then there's visualization layer that uses ParaView and ImageJ. Agave is this platform that actually moves the data between different machines and schedules jobs on parallel computers. So there's basically a scheduler that is moving data around and feeding into. This to me is something actually that I learned about, and the possibilities are quite amazing. Because you have to also be able to log in as a specific user, and different users have different ability to do different things on different machines. And this machine that actually figures out who has access to what on different machines is this Agave platform. And this is the platform where we're in future hoping to actually automate parallel simulation as well. So if one of you, or when I teach this course next time, I'm hoping to click a button and do, for instance, lattice-Boltzmann simulation of flow through one of these images. Wouldn't that be nice? Without anybody learning how to run the software, implement the software, hook it up to their account, it would basically run in this common account and just then get the data and post it back just in that scratch space, and then you can decide to upload it to Digital Rocks portal and make it permanent. Okay? Right now we have a number of people who have decided to do so, so you can actually see the results of their simulations posted online. Okay? So there's this basically, one would have that simulation that would be posted on there as well, and then one could do the full data exploration where you could actually go and investigate petrophysical properties of interest from that platform. Okay. So there's other data repositories that are available. There's Texas Data Repository that has unveiled recently for UT research, so you can upload any type of data there that has been created at UT. There's Energy Data Exchange. Again, any type of data can be uploaded, as well as Mendeley data. Most of these repositories will you upload an archive and you describe it as much as you want. It doesn't have to be in specific format, and most of them will also provide DOIs, so you can cite them in papers and theses that you create. Okay? And then there's this data discoverability bit that you have to work with, and you have to market whatever it is that you build so that people go and use it. If it's not used, it's not useful. So there's actually a number of press coverages. This is one of the most recent ones from TAC, where you can actually read about this proposal. You can see this is data from Dr. Espinoza There was coverage in JPT as well about a year ago, and so forth. And this was built using 2 NSF grants and with the help of Texas Advanced Computing Center. All right, so that covers the database, and it should give you, if you ever end up being a manager and you might in a company and you need to come up with a solution, database solution to host the data and make it useful for different purposes, you will kind of have to think through all of the steps that I have outlined here. Whether it's related to digital rocks or not is actually irrelevant. This is the data management. All right. I hope you find it useful. And we're going to now move through the next lecture. I did post both the new lectures on Canvas, but we're moving on to grayscale filtering. Okay. Where's my desktop? It should be lecture 4 or lesson 4. Oh, there we go. Okay, so this is not 8, it's 4. So we are now moving on to actual data analysis. And before we do any data analysis, we possibly have to clean up the data first. Okay? So we're going to first tackle the topic of grayscale image filtering before we do anything else. So typical process, it goes through acquisition and reconstruction of the data. We have basically covered everything that we were going to say about this. Then you have to do some image processing and filtering. Segmentation is basically identification of objects of interest in your image and some sort of analysis of those objects. So you might do some further processing and analysis. This is typically called morphological processing after you have segmented data or binarized data, and you might extract some surfaces, triangulate, and process it even further. One surface extraction was actually creating that surface that I just did in the remote visualization. And then, so different models, some of them might work with data volume, and some of the models might work with these surfaces, and you should be able, in order to mesh the domain for simulation, and you have to kind of be able to work with both, okay? Or know how to do it both. Now, beware, anytime you filter data, you're trying to lose the data, lose part of the data that you don't like, okay? And there's a little bit of subjectivity to it. Now, if you have a very good image, such as this one, don't filter anything here, okay? Filtering will only blur parts of the image. Now, you might want to blur for some reason to maybe remove some of these small pieces, but it's essentially information loss that you might not want to have here. If you have the infamous data from my PhD, then you have no option but to filter before you actually do anything, because there's everything that could have been in this X-ray image is in there, including rings and too much blur and too much noise, and all that is all bundled into this one. So if you give this directly to any simulator, it's going to choke up and not run for the most part. Okay? So you have to probably filter and lose some of this noise. Now, again, seriously, filtering is information loss. It's been done all the time. So, same thing. In these cases, you typically blur to remove too many details in photos. So any kind of photoshopping is information loss as well. But here we're actually trying to do it for porous media. Now, image histograms will often point out this. We already made this point, but it will point out whether you need to do some filtering. So obviously here, my eyes are seeing two populations, but when I look at the histogram, there's some of it is smoothed out, which means that there's quite a bit of blur in the image and the resolution wasn't good. Okay? Whereas when you have a higher resolution, it's much better in terms of separating. My eyes see two clear populations in this image, and I see them in the histogram. So this is good for analysis. This probably needs some help. Okay? And that's what we're going to learn how to do. So basic image transformation is you might to do some just scaling of the data, rotating the data, and in that case, you're going to interpolate in between the points you have, and we're going to do the exercise to that extent. And the moment you do that, you're going to introduce some of the data into your image that was not there. Okay, so you're going to create some of the data in between the points you have. You might also, let's say that you rotate image, and we're going to do this exercise, and then rotate it back. In that process, you're not going to get the same image back. You're going to lose some information. Okay? So you have to be careful with these things because it's extremely easy to lose the data and as you go through. And I'm going to try to find an example in your day-to-day that you might or might not have noticed. So sometimes you have a Word document, okay? And you import an image into that document. Okay? And you just took a snapshot and you weren't very careful, and then you saved that data. And even though you initially had like a very good resolution image, through the process of importing into your Word and maybe possibly sending it to someone, that Word has saved only a snapshot of the data that was basically resized to the view you had in there, and it lost all of the detailed information. And then when you try to save it as an image later, or enlarge it or something, you actually realize that you have a data loss. Okay? So that happens often, okay? Because the Word has saved itself from, like it didn't want to create a very large file, and it basically just created a snapshot, which to your eyes on the screen it was good, except when later on you wanted to do something with it and the information was lost. So you have to be careful with that. Okay? Now there's a whole, in terms of interpolation, there is actually a number of methods that can actually create a pretty smooth picture. So you can actually create data that is pretty credible, but it's still creating the data based on what you have. Okay. So let's actually do exercise 1. I have to post this for you. Let me just quickly go and send a link to everybody. I need UTBox. So open up ImageJ in the meantime. I have to do this offline or else I can't get to the share area. Let's share link, Control-C, and then Canvas. Okay, go to Canvas and click on the link. and open Fiji or image J. Okay, hello.
It's unavailable to us.
Oh, okay, just a moment. There's multiple settings in box. Okay, people with the link. Okay, try now. UTBox has a dizzying number of settings that you can possibly turn on and off. So take this 90x cropped, for example. That's that actually piece of that image here that we looked at, this one. So just this piece. And before doing anything to the image, duplicate it. Actually, do it twice. And in the same image menu, use transform, rotate, and fill in 45 degrees and bilinear interpolation. And then you can also repeat the process with bicubic interpolation. So bicubic is fitting cubic splines. Now, you want to rotate by 45 degrees and then rotate back. So this is the original image. And then rotate back by minus 45 degrees, right? And you will see some information loss. So there's this, and there's this, then you rotate it back. Because at every point, if you rotate by 45 degrees, it wants to fill in information that it doesn't have. It has things on this 90 by 90 grid that is at 90 degrees, right? So in between those 90 degrees, it doesn't have information. So if you want to produce the information, it's going to fill it in by interpolation, okay?
Does that mean if you just only do it by 90, it'll be fine then?
So by 90, it's not going to have information loss. But by any other rotation, and now if you imagine in engineering, you often have to rotate to align things, right? Coming from different models, because it doesn't have that information. It has information on the grid. And that's true for simulation data as well. You're creating it on a regular grid. Okay. If you want to find out what's here, or here, or here, or here, you gotta interpolate. And you have to create the data. Now, linear interpolation for this point here is just going to use values at these points, okay, to basically figure out what should linearly fit in between, basically just by linear. Drawing a line, it's just that I'm in 2 dimensions. Okay? But cubic will not only use these four, it's going to do a cubic spline, which means that it's going to use the derivatives of this data as well. And we know that derivative at this point using central differencing is using this, and this data, right? So interpolation will then fit a cubic polynomial to the data. Basic. So for these points, it's probably going to use cubic interpolation. It's going to probably use a stencil that is at least 3 by 3, or probably more. So one more layer outside of this, okay? So that's why you're going to get a smoother image by cubic splines. So cubic splines are pretty good in that sense, but they might, on larger data sets, it might be too much work. Maybe computationally too expensive. And beyond cubic, I don't think you have enough data and granularity to go to justify going to polynomials higher than cubic. Okay. So now if I rotate by 45 degrees, I create myself some information in between, and then I rotate it back, I do that process again. It doesn't know that I did plus minus 45 and my result is actually a 0. So in that process, you're gonna now imagine the second problem that you might have in your simulation, for instance, if you're working in cylindrical coordinates, which around the bell you often are. Okay? In cylindrical coordinates, you know that those, as you're going, okay, these cells are getting wider and wider. Angle. So if you're trying to translate this to Cartesian grid and back, you're going to have information loss, especially as you're further away from the center. So note that that's going to be. It's not the end of the world that it happened. Just don't do it excessively. Every time you're going from grid to grid, you're going to interpolate data and create the data. So do. And also, you will also, if I rotate this and I didn't have the data, I gotta fill in, so you will see some empty stuff at the corners where you didn't have the information to fill in. So you can do image calculator and subtract two images. So do original and this 45 minus 45 to see what the loss is.
After rotating the first time the image, and then rotating back again, I don't get the same.
Right, because you had these corners that had to fill in.
Yeah, but
This was done from a larger image. Okay.
so I'm supposed to get the image like this again.
Not precisely. Corners will not be replicated. This is what you got, right?
This is what I'm.
Yeah. So if you zoom in, you can still, in the middle should be the similar. Somewhere in the middle you should have an overlapping. And that overlapping region, you will see a little bit of loss of information. So do image calculator to subtract the two and ignore what's in the corners. Yeah. Yeah, so there's like almost. And you can, as you walk around, you can see what the bad is. They're not going to be huge. But this is plus minus 10. Not a huge deal. But yes, cubic does a better job. So convince yourself that cubic does a better job. And watch with image J, it works with the thing that you click on. So watch that you're working with the original data and duplicate it a couple of times. It's a line, but when you zoom in, you see that it's not as sharp.
Yeah.
And if you want to see the difference, do image subtract the two. And then you can walk around with the mouse and see what the difference is. It's a plus minus 10 on the scale of 250 something. So it's not a huge deal, but it's there. And if you were really, your work was in reactive flow and finding the surface was important, you just lost data. Of course, the most of the information loss happens around the boundaries that you're trying to identify. And with bicubic, it's a better. So I'm not going to say that you should never do this. Do this, just know what the result is. So you can basically put some numbers on what the error is here. So if you do transformations like that and you have some information loss, you should be okay with losing that much information. Or a vary it at the very minimum. Did everybody get this? I think this is essentially... So even something relatively innocent, our brains are trained in math. Math is not concerned by this. Conceptually, if I rotate things by 45 degrees and I rotate them back, I should get the same thing. Mathematically, it's the same thing. In practice, there is information loss. And that's because we live in a discretized world or the world. And this happens with either this image data, simulation data, you name it. You should be aware of this with data. Now we're gonna go through the topic. So this is just a relatively innocent geometrical transformation that can incur data loss. We're gonna then now move on to where we actually want to lose the data. We want to lose the noise, okay? But the key will be that you want to lose the noise and not the data itself. Okay, and there's, of course, a little bit of optimization there because I can't always get things perfectly as I would like to. But there's a certain part of the data that is noisy part of the data that we actually want to lose. So information loss is not always bad. It's sometimes pretty much necessary signals we typically have to clean up before we can move on and do some quantitative analysis. All right, well, see you on Wednesday. And the trip to Dr. Wirth's lab is probably going to be next Monday, so I'm going to keep you posted.